We are doing more SAT math problems, and this one, let's read through it. A company purchased a machine valued at $120,000. The value of the machine depreciates, so it's going to go down by the same amount. As soon as I see same amount, that it's changing by the same amount, that tells me that this is going to be a linear function. And we're probably going to use y equals mx plus b, which is the form, one of the forms of a linear function, a common form that we'll use. So that after 10 years, the value will be 30,000. Okay, so initially it's 120,000, and then after 10 years of constantly going down at the same rate, it's going to be worth 30,000. Which of the following equation gives the value V of the machine in dollars T years after it was purchased? And in these answers, we see a lot of the numbers. That 120,000 was that initial value. There's a 30,000. So because we know it's a linear function, let's get the data that we do have into a table. So just by looking at the variables that they use, I know I've got a t and a v in this table, and t years after it's purchased. So the very first year, it's, well, before, when it's purchased, so which would mean t equals 0, the value is 120,000. And then 10 years later, the value is 30,000. This is enough information to come up with the equation. So we'll use this formula for a linear function, y equals mx plus b, where m is the slope and b is the y-intercept. And luckily for us, this y-intercept is sitting right here. Anytime your input value is 0, then your y-intercept is the output value. So just by organizing our data in this table, we can see that the y-intercept is 120,000. Okay, next we're going to go find the slope, and we'll use our formula for slope. This is the usual formula for slope. It's used whenever you have two data points in a linear function, and you can find how that function is changing, that constant rate of change. And so these coordinates go together, and this is our x1, y1. And these two coordinates go together, and this is our x2, y2. We're going to plug them into this formula here. So for y2, I've put in 30,000. For y1, I've put in 120,000. x2 is 10, and x1 is 0. Now cleaning this up a little bit, I know that 30,000 minus 120,000 is negative 90,000. And I'm going to divide that by 10, which just means I'm going to knock off one of the zeros, so negative 9,000. Okay, so things are looking good. We found our slope. So slope is negative 9,000, which means that this linear function can be represented by y equals negative 9,000 x plus our b, which is 120,000. But x and y really aren't the variables that we've been working with. The problem uses the variables t and v. So this will be our linear function, and it looks like B is the right answer here. So one question that comes up is, how did I know which one goes in which column? You know, how do I know that this isn't V and that this isn't T? Because it will make a difference on your slope for sure. The reason I knew that V had to be this second column, which is the output column, is that's what we're modeling. That's what the function or the equation is going to give us. We have a certain input, T, and it gives us a certain output, V. So that's how I knew the order of these two variables. And you can start to see a pattern. This whole problem is very similar to one that we just did. It's almost identical to this oil and gas production problem where we had to go through and come up with a formula for oil and gas production. So you should expect a problem like this where you're having to construct a linear function based off of a couple of data points. Next problem, let M in the xy plane contain the points 2, 4, and 0, 1. Which of the following is an equation of the line M? So here's my xy plane, and here's the point 2, 4, 1, 2, and then up 4. And the point 0, 1 will be right here. So there's some line that goes through these 2 points. And the question they're asking is, which of the following is an equation of line M? So here's line M right here that connects these 2 points. When we want to construct the equation of a line, or in previous examples, a linear function, this is sort of our go-to formula here, y equals mx plus b, where m is going to represent the slope of the function and b is always the y-intercept. And luckily we have the y-intercept sitting right here. The y-intercept is the point where the function or the line crosses the y-axis or the vertical axis. So from this point we know that the function crosses the y-axis at y equals 1. So whatever else happens in our formula, we know that b equals 1. This b right here. Now we're going to go ahead and find the slope, and we'll use these 2 points right here. Slope is always represented by a formula like this, where it's the difference of your output values over the difference of your input values. And so we can call this point right here our x1, y1, and this point right here our x2, y2. And so now I'm just going to put in the actual numbers. y2 was the number 4, y1 is this y value over here, x2 is this number right here, and then x1 comes from that very first x coordinate. And we'll clean this guy up. So we've got 4 minus 1 is 3, and then 2 minus 0 is our 2, and this is our slope. So that's awesome. We've got our slope and we've got our y-intercept already, so we know that y should equal 3/2 x plus 1. And it looks like answer D is the right answer here. So again, once we know that we have a linear equation or equation of a line, the 2 points are all we need. We'll find the y-intercept, and luckily it was sitting right here. And then we found the slope in between these 2 points, and we're able to put it back into the formula like this. This one's really similar to the last problem we did. It's just not in the context of some story problem. It's just, here are the numbers, figure it out. Okay, next problem. This one has so many words, and it actually looks worse than it is. It's not too bad. We've got a graph here that's going to relate years since 1940 to minimum wage. And so these dots represent the actual data. And then the line is called a line of best fit. It's like an approximation of the line that would represent closest to what's happening with this data. So the scatter plot above shows the federal mandated minimum wage every 10 years between 1940 and 2010. A line of best fit is shown, and its equation is y equals all that, 0.096x minus 0.488. What does the line of best fit predict about the increase in the minimum wage over the 70-year period? And then we've got these 4 options. So before we dive into all the possibilities here, let's review what this really is. This equation is an equation that looks like y equals mx plus b. We've got our m here and our b here. And we remember that slope is the m and the y-intercept is the b. For a linear function, slope can be thought of as how the function grows, or maybe it's going down, how it goes down, or how it declines. But slope is how this function is growing. And the y-intercept represents how it starts, how the function starts. So this one, the y-intercept isn't even on the graph for the line of best fit. It's down here somewhere. But we do know the y-intercept is this negative 0.488, which isn't even represented by the picture, and the slope is this 0.096. And so that 0.096 is telling us how this is growing. What that means is for every 1 year we go to the right, the minimum wage grows by 0.096. So for every 1 year, the minimum wage is going up about $0.096. So as I look at these answers, I'm suspecting that A is the right answer. Each year between 1940 and 2010, the increase in minimum wage was $0.096. That is going to be the right answer. Let's figure out why these guys are not right. Each year, the average increase in minimum wage was $0.49. No, the $0.49 is the y-intercept, so that's not right. Every 10 years, the average increase in minimum wage is $0.096. No, even though they give us this data every 10 years, when you're talking about slope, it's for every 1 unit increase. So for every 1 year, how is the function increasing? And so that's kind of tricky, and then D is wrong for a bunch of reasons. So A is the correct answer, and this is why. We didn't really have to do any math, but we did have to know what each part represented in this function. This problem has a lot of similarities to the last problem, and this is the one that's relating, let's see, temperature to sales of ice cream. And it's another scatter plot one with a linear function. So go ahead and try this one on your own. And then on the next video, we'll do the worked out solution together.